Okay, could I have everybody's attention, please? The University of Wisconsin Peer Learning Association has started some study groups with various psych classes, and some of you are in it. How many of you have been to any of their meetings? I'm seeing 5, 10, 15 people's hands up. How many of you filled out their survey and requested information from them? And did anybody not hear back? If you're interested in joining a peer study group, please write Andrea at this email address, and I'll be sending some further information out to you also about that to help you kind of practice sort of your study methods and so forth. If you want to go over your exam in a kind of a structured way, you can please see Shin about that and write him and make an appointment to do so, and maybe you and I could talk afterwards about that. Okay, Shin? Is that all right? All right. Today, our topic is research methods. Research methods is not everybody's favorite subject, but it's an important dimension of the science of psychology, and I'll be sort of making the case in this review today that psychology is a science, and that we'll sort of talk about what that means and explore some of the issues. Okay? Would you do me the favor of closing the doors in the back, please, Shin? So the review of research methods, as this first slide indicates, is really about how do we infer from observations? How do we make conclusions based upon what we've investigated? And what are the kind of the problems that are associated with inference and knowledge in general, in science and kind of more largely in society? So I'm going to begin with the topic of scientific knowledge and just sort of make the claim that what science is a very particular method of going about making observations. Now, this is something we all do every day. We make observations and we reach conclusions from our observations. So science is not different in a way from what normal life is really all about, except that it involves a particular kind of systematic manner of observing and a particular kind of effort to exert a form of control over what we're observing. And if we engage in this systematic and controlled form of observation and reach inferences from those observations, we can come to tentative conclusions that can then be revised as we examine the implications of what we've observed. So overall, it's a kind of an iterative process of investigating, trying to reach reasonable conclusions about our investigations, but then altering our methods and making further observations to refine what we know. I think that measurement in general in social science, which includes political science and economics and sociology, the whole, actually it extends into the medical arena as well. All of medical science really is about what psychologists have called construct validity. Construct validity is the investigation of constructs. What is a construct? A construct is ultimately an idea. Personality is an idea. Emotion is an idea. Empathy is an idea. Intelligence, schizophrenia, manic depressive illness. All the things that we are interested in are fundamentally constructs. They're ideas that we want to investigate. When we go about trying to measure our ideas and have measures that correspond to our constructs, we can take, for example, how all of the personality tests that you took were essentially measures of individual differences. They were, and the big idea there is that people vary on important dimensions that matter to their own experience of themselves, but also to how they act, feel, and think. So that all of our personality tests were endeavors to measure individual differences, kinds of constructs, and ultimately the tests are what I call construct probes. They're efforts to kind of explore the nuances of the constructs, explore the nuances of what is optimism. Well, the Lot R and the attributional style questionnaire, which are different measures of optimism, are not the be-all and end-all of what optimism is all about. All of that research that we looked at about the nature of optimism and what does optimism do to people's thoughts, to their feelings, to their actions, is what the big idea is all about. How does it relate to health? Constructs are really very, very big ideas, large kind of struggling thoughts that society has and that scientists explore. All constructs, the measurement of any idea that you have, gross national product, the whole idea of profit is a kind of a construct in a way, involves measuring variables. And the same principles that we talked about the essence of principles of personality assessment are the measures that go into studying all kinds of measures, whatever it is, whatever idea you're pursuing. You need to have a standardization of conditions of measurement. You need to create some kind of a measurement context, whether it's a test or an observational context, and you standardize those conditions. And oftentimes associated with that standardization, if you have tests, you develop norms that are associated with standardization, and then you explore the reliability of your measures. Are your measures repeatable? That's what reliability is ultimately, is can you repeat the observation and get the same result or not? And then ultimately the question then is, okay, even if we can develop a good measure that has good norms and is reliable, is it useful? Validity is about utility and usefulness. Does it predict something? Can we make a prediction based upon the test or our assessment? And then once we make that prediction, what do the data show about its value ultimately to us? Albert Einstein claimed that, made these comments here, not everything that counts can be counted, and not everything that can be counted counts. I like that one, although most of science is pretty quantitative, and psychological science is that way also. But we also realize that the ideas, the essences of the ideas that we're interested in sometimes defy quantification to a certain degree also. And ultimately, that science is about a refinement of the everyday thought process. Ultimately, it's a systematic and controlled method of exploring your observations and refining them really over time. It's kind of what we're all about. We're going to be focusing today on two major classes of research methods. One we'll call the descriptive research methods. The second one is experimental methods. And I want you to make a clean distinction between descriptive research methods and experimental methods. Descriptive research methods are typically discussed in terms of having kind of four separate types of descriptive research methods. The case studies, so-called naturalistic observation, surveys, and correlations. We're going to spend most of our time on correlations. But to kind of work our way up to that point, case studies are in-depth individual analyses of particular persons. The case studies that you read about in Oliver Sacks' book, The Man Who Mistook His Wife for a Hat, all of Freud's work, really ultimately, all of clinical science, in many ways, gets grounded in applying things to individuals. Case studies are excellent context for being able to flesh out descriptively what's going on with particular individuals in particular scenarios. But ultimately, case studies are case studies. They only tell us about particular individuals, and we can't often see the mistakes that we're making in reaching certain conclusions about individuals. Jane Goodall, who studied the chimpanzees, I believe there's a movie coming out I saw a trailer for called Chimpanzee coming up at some point this next year, is about Jane Goodall. People who study animal behavior in the wild are called ethologists. Ethologists study animal behavior in naturalistic contexts, and they try to describe what animals are doing. Naturalistic observation is an important method in psychology, going out and watching what people do. If you want to understand how gangs operate, you're going to have to go hang out with people in gangs and follow them around and see what they do. You're probably not going to be terribly satisfied with trying to create a gang simulation using undergraduates in the laboratory in the psychology department to understand gangs, are you? It's going to be like, hey man, that's not it. So naturalistic observation is critical. Survey methodology, we see this all the time in the news. We're being surveyed to death. We all know that. You know, political polls are all about surveys with margins of error and so forth. And then finally, correlational methods. And I want to spend a lot of time on correlational methods because correlational assessments are often the beginning point for a series of further studies. And I want to talk about kind of how that develops. So let's begin with the idea of what a correlation itself is. A correlation itself is a mathematical representation. Basically, a correlation coefficient is a number. That number varies from -1 to +1. And the closer the number is to the absolute value of 1, that is, the closer it is to -1 or to 1, and the farther away it is from 0, the stronger the degree of relationship there is between two variables. Let's take a look at a few examples. Before we do so, the key and critical element is that whenever you have a correlational study or a piece of knowledge that's based upon observation of what two things go together, and that's a simple way of thinking about what a correlation is. What goes with what? And to what degree do they go together? It's a quantitative representation of the degree to which two variables co-vary over time. When you measure one thing, you can get an idea of how the same individual would show up on another measure. That's essentially what a correlation is. Correlations, as useful as they are always insufficient ground for reaching conclusions about causes, because correlations by their own nature are uncontrolled. We're just measuring what goes with what, and we can't separate out all of the factors that explain that association. Correlations are descriptive. They give us a good idea of how two things go together, but they don't give us a good idea about why those two things go together. So the question of why, the question of explanation, is a question about the nature of causation. And correlational data suggest causes, but they don't give us enough information to reach causal conclusions. And that's going to be an essential item for you guys to be very clear about when it comes to exam questions and so forth. Okay? Essentially, correlations summarize data that can be represented in what are called scatter plots. A scatter plot, as is shown in this edition of your textbook, just is a series of points plotted around two variables. If there's a perfect relationship between the two variables, you have a perfect negative relationship, all the dots line up, all the data points line up in a very precise pattern on a single line. This would be a -1 correlation, item on the other side, a perfect positive correlation, where there's a perfect association. If we had no error whatsoever in our measurement, if you measure something in the metric system versus the non-metric system of measurement of a length, if you had perfect measurement, you'd find that they correlated perfectly. Now, actually, since there's human observation and human kind of processes involved, even outstanding measurements have a level of unreliability to them. If there's no correlation, you see a scatter plot where the points are all over the place, and if there's moderate correlations, you see some degree of scatter, which is typical in general. Most of you took some version of a college entrance exam. This version is called the Scholastic Aptitude Test. Why do admissions officers use these kinds of tests? Because they tend to predict success. People who score better on the exams tend, on average, to do better in college. And if you've got 30,000 applicants and you're only going to pick 6,000 people, how are you going to go about making a decision? This is an economical way of doing it, and the problem is what, however? Error. The fact that many people who get very good scores on these exams, in fact, don't wind up doing all that well in college. And there are people who don't do well on the exams who are outstanding students. There's error involved. It's an imprecise science, very much. You tend to sleep less as you get older. What's the cause here? What causes what? Does getting older make you sleep less, or does sleeping less make you get older? Well, these are the kinds of questions we're going to explore a bit more closely in a moment. This is a silly little one here. Is there a relationship between number of house plants that people have in their home and how often people brush their teeth? This fantasy example is no. That's an uncorrelated set of observations. I want to briefly talk about statistical significance, which is discussed in your textbook. Statistical significance in correlational and in experimental research is something you should sort of begin to get familiar with, and of course you'll have a whole series of classes on this in your statistics courses if you kind of take that next step. But I want to give you a little bit of a sense of it right now. The typical way that statistical significance is described in journal-level research is in terms of these expressions: p less than 0.05, p less than 0.01, p less than 0.001, p standing for probability. And what these expressions refer to is the likelihood, the probability, that the observation achieved, the particular correlation coefficient or the particular experimental result, refers to the degree to which that observation is likely to have occurred by chance. Statistics imagines a situation where we could repeat an observation an infinite number of times. We could repeat measuring two correlational variables in different samples an infinite number of different times. In reality, we don't have an infinite number of different times to do anything. We usually have a sample, and sometimes we could say, in our instance here, we'll say we'll start out with 100. And imagine that you did the experiment 100 times, or you made the correlational observation 100 times. Statistics is a way of saying, well, you know what, that result that you got that you're real happy about and looks really great, it is possible that that's a complete, absolute fluke, isn't it? And that you got the results that you got because of chance. This expression, p less than 0.05, is a mathematical expression of the idea that the result that you got is unlikely to have occurred by chance alone. If it was due to chance, you'd only get this result 5 times out of 100. So it's kind of a measure of confidence. Statistical significance is a measure of confidence in your measure of the construct that you're attempting to measure. P less than 0.01 means that your data tell you that you would have only gotten this particular result one time out of 100 if it was due to chance alone. And every social scientist's favorite number is P less than 0.001, suggesting that your data are so good that it's unlikely that you would have gotten this result by chance. That chance result would have occurred less than one time out of 1,000. That's what P less than 0.001 refers to. So do you get the idea of statistical significance? It's a representation of the likelihood that an observed result would occur by chance. Any questions about that? Now, a significant correlation suggests overall that it's reliable. It's probably going to be reliable, and it might be valid also. So you begin assessing measures by attending to statistical significance of the measure, but then you investigate the meaning of the measure. Good measures are repeatable. They tend to be, just go back here. They tend to be repeatable. A predictable result will allow you to begin to make predictions about other variables in a way that you can count on. But I want to leave you with a point and have you kind of hold it very clearly. Just because something is statistically significant doesn't mean it's practical or of any real theoretical value. Not really. I want you to make an asterisk next to that remark and realize that I've said it, and hint, hint, wink, wink, maybe this one will show up on an exam, do you think, huh? Just because something is statistically significant isn't enough to conclude that it's useful, valuable, important, necessarily. You need to be critical about measures, even measures that appear to be statistically significant, because there can be other explanations going on. Now, I want to talk about two essential big problems with correlational research. And these problems have to do with the temptation that researchers and students and reporters have to draw causal conclusions from correlations. And this is going to get a little bit into kind of a sort of a philosophical analysis. And there are two main reasons that you can't infer a causal association from a correlational result. And these two reasons are, put simply, the directionality problem and the third variable problem. And I'd like to talk about those in sequence, the directionality problem and the third variable problem. Let's take the situation where we've done a study, and let's say we have 1,000 individuals, and we measure the degree to which people have sleep problems and the degree to which they have some measure of depression, which we've studied, let's imagine that we have a measure of depression. A measure of depression and a measure of sleep problems. And it turns out that they're significantly correlated, statistically significantly correlated at the P less than 0.001 level. The observation is very unlikely to have occurred by chance alone. People who are depressed tend to have sleep problems, and people who have sleep problems tend to be depressed with some error of measurement in there of some amount. Does one thing cause the other? Does sleep problems cause depression? Does depression cause sleep problems? Depending upon who you are, you're going to have a bias to want to explore those different ideas. So if we just sort of look at this in a kind of a figure form, what I called earlier the directionality problem is represented in the upper two aspects of the panel of this figure. The directionality problem is such that you can't infer causation because of one thing, of one variable to the other, because let's imagine that we're saying, I think depressed mood causes impaired sleep. Imagine that I have that as my theory. I think that depressed mood causes and creates sleep problems. And I go out and I measure a lot of people, and I measure the level of depression, and I measure their level of sleep problems, and I get a significant correlation. Let's imagine that it's even as high as 0.5. Does that validate my theory? And why doesn't it? Well, it's evidence that doesn't contradict my theory, and I might be tempted to want to interpret it as supportive of my theory, but the problem is that it's every bit as logical that depressed mood is caused by impaired sleep as it is that impaired sleep is caused by depression. It works both ways, and you can't tell the difference from a correlation. So you can't infer a causal relationship between two variables from a correlation because of the directionality problem. Does that make sense? Anybody have any questions about that? Any confusion? Similarly, on the bottom panel here, we have a situation where maybe it's the case that both variables, depressed mood, and impaired sleep, are caused by something else. This is the third variable problem, that just because you have a significant correlation doesn't mean you can create any kind of causal statements about it, not only because you have of the directionality problem, but also because of the problem that maybe it's the case that some other single or set of variables causes both. That this panel suggests depressed mood and impaired sleep neither cause the other, but both are caused by, in this case, family conflicts, or maybe genetics, or maybe socioeconomic conditions. And you get the idea that we can all generate many alternative possibilities, can't we, about what accounts for this association, right? Let's take another example that's going to come up throughout the class. The relationship between a certain form of psychopathology that we're going to call depression here, and the level of central nervous system neurotransmitters, norepinephrine and serotonin. There is a theory that I think I referred somewhere in the notes as the biogenic amine The biogenic amines are a group of neurotransmitters. The biogenic amine theory of depression states, in its simplest form, that depression is caused by a low level of norepinephrine and serotonin. That's the biogenic amine theory. The biogenic amine theory grew out of correlational assessments that are similar to the one that I'm going to show you here in a moment. So how would you test this theory? If you're going to test it correlationally, what are you going to do? You're going to go out and measure a whole bunch of people with respect to their level of depression, and then you're going to take a sample from their cerebrospinal fluid and measure the so-called metabolites, which we'll talk about what a metabolite is at a later point. You can't go into people's brains and measure their level of norepinephrine and serotonin. What you measure is the indirect byproducts of that in the kind of waste products. So you measure the cerebrospinal fluid and you find out what the level of norepinephrine and serotonin metabolites are, and then you get a guess as to how much is going on in the brain. So take a look at this little slide. What kind of a correlation is represented in this figure of the level of norepinephrine and 5-HT metabolites? NE stands for norepinephrine, 5-HT stands for serotonin. We'll talk about norepinephrine and serotonin again many times in the course of this class. And here we have a simplified representation of level of depression, and we won't go into the measurement scheme here, but let's say we have 1,000 cases, and we measure it, and we have a scatter plot that looks sort of like this. And what kind of a correlation is going to result from this computation? Is it going to be a positive correlation or a negative correlation? It's a negative correlation because you can see the slope is going this way. And the idea is what? That these two things tend to go together on average, with a bit of slop in there also, right? So recognizing the slop, the biogenic amine theory of depression would state that, going back to it, would be what? Would say that this is evidence in support of my theory that lower levels of norepinephrine and serotonin cause higher levels of depression. That's a causal statement from a correlational result. Everybody agrees with that, right? You get how that's a particular statement of direction. But what's wrong with that, given the directionality problem? So what would it mean to say it the other way around? Direction one, the people who brought you Prozac want to sell billions of dollars worth of pills to millions of miserable people, or people who maybe aren't even as miserable as they think they are, but, watched the ad, and the ad said, ask your doctor if it's right for you. And they decided, well, I better go find out. Maybe it is right for me. And they get the prescription and take the drug, and maybe they feel better. The direction one is that my depression was caused by this low level of norepinephrine and serotonin, fitting the biogenic amine theory of depression, just like my doctor said, based upon a correlational result, right? Everybody seems kind of happy. But what would direction two be? So imagine if you were an advocacy group saying, wait a second, let's take a look at this critically. What is the nature of the data that we have? What statement would you make to say it the other way around? This direction one was low levels of norepinephrine and serotonin cause depression. That's direction one, right? What would the other causal statement be? Depression, maybe it's the case that your level of depression causes the metabolic difference. Maybe there's a psychological effect on a biological variable rather than the other way around. Does that seem crazy to anybody? Or does it seem reasonable? Do you see the point? They're very different, aren't they? They're very different conclusions from the same data, neither of which is warranted from the correlation itself. The correlation doesn't tell you, what I'm trying to teach you is that concluding either of those would be an error. You can't tell from the correlation. All you can tell is that these two things tend to go together. There's something going on. That's what you get from a correlation. The third variable problem would tell us what? Well, maybe even if there is a causal relationship, and personally I am convinced that there is, and I'm convinced that it works both ways, that people who have larger levels of depression tend to have these metabolic changes, but it's also the case that there are genetic predispositions to the synthesis and utilization of norepinephrine and serotonin that have a causal impact on depression. But let's take the example of the sleep studies. Does depression cause impaired sleep? Well, yeah. Actually, it's a symptom. It's one of the symptoms in the assessment of depression. But is it also the case that impaired sleep causes depression? You bet. People with sleep disorders, I had a number of years ago when I weighed 65 pounds more than I weigh right now, and my family couldn't stand to be in a motel room with me because anybody know where I'm going with this? Have you experienced that with your own family? It's like loud snoring people in a room with you, oftentimes because they weigh too much. Some of them they're sort of chortling away. Well, that was me, and I think that my impaired sleep turned out I had a sleep study, and I was also depressed and irritable and, having kind of alcohol abuse problems and other things too. And I discovered that my sleep problems were creating the mood in addition to the mood creating the sleep problems. It really does work both ways. And sometimes if somebody's depressed, it's important to find out, how are you sleeping? Do you have a sleep disorder? I had a test done, and the test showed me, the sleep study showed me, that I was waking up 45 times an hour. My brain was. I mean, I know consciousness of that, but it was like when you have sleep apnea, which means not breathing. Apnea stands for not breathing. Your brain, you're sort of starved for oxygen, and your brain sort of startles itself into a new level of alertness where you move a little bit, and so you get oxygen. And that was a very serious problem. So you get the idea that, maybe it's not, in all of these cases, the directionality problem and the third variable problem require us to be cautious in our interpretations about the nature of the meaning of a correlation. That having been said, descriptive correlational data help us with causal understanding. They're often the beginning point for causal studies, for saying that, well, these two things go together. Let's do some more studies to find out in what way does impaired sleep create depression? In what way does depression create impaired sleep? In what way might there be a causal impact of norepinephrine and serotonin on depression? And in what way might it be the case that psychology affects brain chemistry? The other way around. Let's look at them both. And let's look at how social conditions, the third variable problems, social conditions, genetics, marital conflict, alcohol and drug abuse, other kinds of issues are also part of the story. Most knowledge begins with noticing correlational associations, and sophisticated work in social science and psychology involves multivariate correlational work. So you're looking at many, many, many variables simultaneously is the essence of what multivariate correlational research refers to. And we'll develop models of how does family, marital harmony, drug abuse, economic conditions, and genetic profile, how do those model together in terms of the likelihood of creating depression? Theory development, hypothesis testing, and experimentation often begin from good correlational observations. Okay? So that's my section on correlations and descriptive methods. Now we're going to end on talking about experiments. What is the difference between an experiment and a descriptive study? Just kind of wake everybody up briefly here. I see some people recognizing themselves as being the nodder offers down here. Go, oh yeah, that was me. So stretch. If you need to stretch, stretch. Experiments make an effort to account for other variables. That's one of their chief values. They make an effort to account for other variables. Experiments are our best known method for inferring valid causal relationships between variables. You'll see in many textbooks that they're really our only way, scientifically. It's the scientifically tested method of discerning when you have a cause is you have to do an experiment to find out. Most studies are kind of stuck with correlations because some things we just can't manipulate very well. So I want to talk about this idea of the value of experiments and inferring valid causal relationships. The core features of an experiment are ones that are elaborated in further bullet points, and those are going to be the presence of an independent variable, the presence of a dependent variable, some kind of an effort to have a random sample from a representative population, and then within that, random assignment from that random sample to experimental conditions. That's what we're going to be talking about. And throughout all of that, experimenters make an effort to do their best to control extraneous irrelevant factors. So to get us started, let's go with our definitions. An independent variable is what? You can probably all define it, perhaps not in exactly these terms, but so let's practice getting our terms together. An independent variable is a variable that is manipulated or controlled by an experimenter. That's what it is. It's the variable that the researcher controls and alters to see if there is an effect of it. The experimenter controls the independent variable. For those of you who are interested in the language of experimental design, an independent variable is not free to vary. It's fixed. It's under the control of the experimenter, it's fixed by design, and it's not free to vary. That stands in contrast to a dependent variable. But let's have an example here to get the conversation going. Back in 1977, Rush and a group of other people in Philadelphia placed a newspaper advertisement in the paper, and they said that they were going to do an experiment or a study examining treatments for people who are depressed, treatments with a form of therapy that was then being kind of developed and touted called cognitive therapy, and comparing that with antidepressant medication. So they put an advertisement in the newspaper and asked for people to write them to join the study. So that was their sample. How's that for a sample? People applied to respond to a newspaper advertisement, and then the experimenters interview them carefully and pick the ones that they want to get it started. What kind of a sample is that? Is that a random sample? Sure isn't. Most samples aren't random. All right? Are you all random? You're going to be involved in experiments here for extra credit. Are you a random representative slice of modern American society or not? Absolutely not. There's a lot of stuff. So this is a big problem. Getting actual random samples is hard to do. And getting representative samples is hard to do, too. But that's the way the cookie crumbles, as my grandmother said. That's the way often research is done. That was their sample. Then then what they did is they took the people who applied and they randomly associated them. They randomly assigned them, to 3 different treatment conditions: a placebo condition, an active medication condition, and a cognitive therapy condition. 3 different conditions. Okay? So that was the independent variable was what treatment were the people getting in that previous study. Then after 3 months of getting twice a week cognitive therapy or 7 days a week medicine or being on a placebo wait list control group, in other words, they were told that we don't have enough time and resources to attend to you now, but in 3 months we'll be able to help you. So people had the expectation of getting some help down the line, but they were put on a wait list control group. That was the placebo group. Let's measure what shows up after you do the study. A dependent variable is conceptualized as depending upon an independent variable. Theoretically, a dependent variable is free to vary. In other words, it's unconstrained in its outcome, And if your theory is right and it's connected in some reliable, valid way to your manipulation, then even though it's free to vary, you can wind up making some conclusions about what caused it down the road. Dependent variables are hypothesized to be possible effects of independent variables or caused by those independent variables. In the Rush et al. Study, they measured after 3 months the level of depression in the persons who had been in any of the 3 conditions. Those persons were equivalent in their level of depression when they were randomly assigned to the 3 conditions, and then they were measured later for their level of depression. And for some reason my thing isn't changing. Here we go. The experimental data from the study showed essentially 2 data points. 60% of the people who were in the cognitive therapy group were rated as not depressed at the end of the 3-month trial. 60%. So you guys should be writing this down. You should be writing everything down that's not listed up there. 60% of the people were identified as being not depressed. In the placebo waitlist control group, 30% of the individuals were listed as not depressed afterwards. Okay? So that's the sum of that experiment. What can you conclude from that? Kind of a tricky point has to do with the placebo. Was the placebo entirely a placebo? There were other things going on, weren't there? All those people expected treatment down the road, for one thing. There was so what's confounded with this, with the placebo result? There might be a temptation to say that the expectation of getting treatment reduces depression over a 3-month period of time. But we don't have a no treatment control group at all, do we? Without that kind of placebo expectation. So that 30%, some portion of it is due to what? Some portion of it is due not to the placebo as much as it is just to time. If you wait long enough, people get better, no matter what. I was contemplating getting back surgery a few years ago. My brother-in-law said, his radiologist, he said, well, the research literature suggests that 2 years after surgeries, there's no difference between people who get the back surgery and people who don't. So, and there's a lot of problems with back surgeries. So his recommendation was, wait. I waited. My back is fine now. I'm really glad I didn't have somebody chop up my back. How about the 60% not depressed from the medicine group and the cognitive therapy group? Does that sound significant to you versus 30%? It's a pretty big difference. But do we know why people got better? We don't, do we? Yeah.
Just to clarify, there were 60% in the medicated group.
We're not depressed, and 60% in the cognitive therapy group were not depressed. So you can't tell the difference. What caused it? Well, the only thing that's reasonable to conclude from this study at all is that these 2 treatments are better than placebo. But we don't know why they work. That's all we get. Oftentimes, the results of experiments are very limited in terms of what their particular specific value is. They tell us a little bit of an important story. Okay? We don't know why the cognitive therapy works. We don't know why the medicine works. We don't know what it was about time versus placebo that caused the change for the so-called waitlist placebo control group. A lot of things, oftentimes more things are unknown at the end of the experiment than are known. Good experiments generate lots of questions. Okay. This morning, I mailed you a very short article that I'm going to talk about now and that you can look at afterwards, okay? I'm going to talk about the experiment right now. I call it the seeding experiment. And even though it's not on your syllabus, but it's now an assigned piece of reading. It's 3 pages long. Everybody can do it. All right? But I'm going to talk about it with you right now. The particular experiment studied students in a large physics class, 200 students in a physics class at the University of Colorado. I think it was not the physics class for physics majors. It was the physics class for non-physics majors class. That was the context of it. And the article begins with a professor making a claim. He says something like, every physics professor knows that the best students sit at the front of the room. And that's how it started. The students who sit at the front of the room get better grades, and they're better students than the students who sit at the back of the room. Okay? That was the claim. Now, that was this guy's experience, and it was a set of beliefs that better students sit in the front. If you ask around, you'll discover that lots of professors in lots of different disciplines say, yeah, that tends to be the case, that the people who sit in front wind up doing a little bit better than the people who sit at the back. People who sit at the back are more likely to be surfing the internet, doing texting, paying less attention. They don't come to class quite as regularly as the people who sit in front. There's something different about back of the room people versus front of the room people. This is a correlational observation, isn't it? It's just, I noticed this to be the case, that there's an association between grades. Actually, I meant to write a question that I forgot to do it. I could have studied that with our own data. If somebody reminds me, maybe I'll do it next time. Like, where do you sit in this class? Could you identify yourself as being in the front of the room, the front, back, or middle of the room? You have a sense of where you'd rate yourself? Front, back, or middle? Everybody sits in the same seat all the time, right? For the most part. Hardly anybody ever moves. I started returning papers and I had a class of 30 people, and I graded their papers, and I started putting them on their desks upside down before they got there. And I was right all the time. That people sit in the same place. They just tend to. What's wrong with this observation, do you think? Say what? There's error, okay. There's lots of random error as part of it. Is it? So maybe I can just sort of jump to the chase. They decided, let's do an experiment. Let's make people sit a certain place and see what happens. So what they did is they randomly assigned people to 4 levels of distance from the front of the room. They measured it out like good physics professors in terms of meters, how far away from the front of the room they were. You know, group 1, group 2, group 3, group 4. And they measured the distance from the front of the room, and they randomly assigned people and to sit there, and they had a seating chart, and that's where you had to sit, otherwise you would lose points. If you were gone, attendance was taken, right? You had to be there. If you weren't there, it was known that you weren't there in the room. So the independent variable here is what? Distance from the front of the room, seating at the beginning of the semester. At the mid-semester point, they flipped things around. The people in the front were now in the back, and the 2 middles got flipped from side to side too. The method of seating assignment was what in this class? Was it random? I mean, the physics professor's view before, I mean, what was their view based on? Good students sit in the front and they ask more questions. They seem to be paying better attention. You have to call them out less for having conversations than the people who are farther away. It was based upon a correlational association. What they did in the experiment was manipulate seating location. So the independent variable is the manipulation of distance from the front of the room based upon particular measurement. And then they measured attendance and grades. And those are the two things I'm going to talk about, attendance and grades. At the attendance level, it's a small difference. It's a strange study in some respects. They have the first half of the term and the second half of the term. But I'm going to simplify this graph and just make the following claim to you: that the people who were randomly assigned to sit at the front of the room wound up at the end of the semester having a much better attendance record than the people who were randomly assigned to sit at the back of the room in the beginning. So their attendance was better, number one, and, as this little blow-up suggests, on average, and that's an important qualification, on average, there was plenty of people who got bad grades in the front and good grades at the back, but the association was such that there was a tendency for, if you sat in the front, you had a higher likelihood of getting a better grade than if you sat at the back of the room. That's what they found out. What can you conclude from that? What are you willing to conclude from that? You don't need to be particularly bold.
There's a correlation between...
No, there's not merely a correlation. There is a causal association between distance from the front of the room and grades and attendance. There's a causal association. They demonstrate that because it's an experiment. It's not merely correlational anymore, is it? They manipulated distance. Where you sit has a partial causal impact on your attendance and your grade. Nobody wants to believe that, do you? But that's all that can be concluded. Do we know why? We have no idea why it works out that way. We can all come up with kind of clever theories, but those theories need to be examined in subsequent research. What we know from this study is that in this particular kind of physics class at the University of Colorado, so if we're going to be particular, we've got to narrow it to that context, right? That seating location bore a causal association with attendance and grades. Not that it was the whole story by a long shot. There's plenty of other things going on, like people's interest in physics and their and so on and so forth, and their ability levels, lots of other causes. But where you sit matters. It actually matters. Now, why might that be? I'm not going to belabor the point, but what would a quick set of observations? Why? What's the causal relationship all about? What does being closer to the professor have to do with anything? Does you soak up good grade points, by you're closer, Does that help you somehow? What is it about being closer? Hear better? Okay. So hear better, see better. So maybe, and this is something that needs to be studied, maybe sitting closer increases attentional focus and facilitates screening out distractions. Maybe. Right? And maybe the closeness also has something to do with, they know who I am, they see me, I think I'm a known quantity, and I can't not show up. But it does something, maybe it also increases interest. Who knows? If you're paying attention and stuff is interesting and you feel like you're known as a human being, are you more likely to want to come back? becomes more interesting. If you sit in the back, it's easier to space out and kind of think about lunch, and think about other stuff. It's easier to kind of say, well, they don't even know who I am, so I don't need to come back. But all the experiment tells us is that there's a cause of some kind. Okay? I asked you to read a very difficult study, and if you haven't read it yet, I'll go over it with you now. By Davidson. Richie Davidson is a researcher here in this department, and they did a study examining the relationship between participation in a mindfulness-based stress reduction program and a variety of other things. So they manipulated which group of people in a work setting were in the program versus which people were on a wait list control group, saying, we don't have enough time for you now, but we'll do it for you next time. So the independent variable was, were they in the meditation program or not? The dependent variable that they measured and they hypothesized about was that people who were in the meditation program, the mindfulness-based stress reduction program, one component of which is the exercise that we did in here before about attending to pleasant and unpleasant events and learning how to really allow yourself to sink into positive feelings and to allow yourself to explore and really notice negative feelings, really take the time to notice them. The people who were in the meditation group had a decrease over time in self-reported negative affect, less anxiety, less negative emotion in general, associated with the mindfulness group by self-report. They also found, by doing some fancy brain studies that we're going to talk about later, that there was an increase. The people who were in the meditation group had an increase in average activation of their left prefrontal cortical tissue. So there was a shift for the meditation group such that there was more activation of their left prefrontal cortex over time compared to the waitlist control group. And finally, they did a manipulation where they expected there to be a relationship between the immune system and meditation, and they gave people a flu vaccine, and they discovered that the people who had been in the mindfulness-based stress reduction program, the meditation group, had a more robust and powerful reaction to the flu vaccine. They had an increase in what were called antibody titers, meaning they had a more robust and powerful immunological response to the flu vaccine. These are the three main dependent variables that demonstrate to these guys' satisfaction or to their argument that there is an association between mindful meditation and the kinds of things that people who engage in mindful meditation do in life. They practice patience, acceptance, letting go, non-judgment of self and others. Those 7 qualities that we went over before. You guys remember that from the previous lecture? People who do that wind up getting less unhappy, having the positive, happy side of their brain increase in its activity, and their immune systems get more powerfully present. Now, it turns out that there was a confound in this study that everybody has to live with, and it's sort of cleverly disguised in a certain way, in which confounds tend to be in published papers. But a confound is an uncontrolled variable. So that there was something about the control group, the waitlist control group, that wasn't in fact the same. A good control group, everything is the same except for the manipulation of the independent variable. There's nothing else is different between the groups. So a confound is a variable that has been unaccounted for and that systematically differs between the control group and the experimental group outside of the experimental manipulation. So it's an unaccounted for variable in a way, it's an alternative explanation for the results. Another thing happened. In this study, the people who were in the mindfulness-based stress reduction program had a meeting once a week for 2.5 hours during work, where they learned about the principles of the week, and then they left the group, and they had a group experience that was kind of fun for the most part, and educational and kind of feel-good kind of stuff. And then they left the group, and they practiced meditating and practiced principles outside of the group context. But the people who were in the experimental group, they had to go to work the whole time. So that little thing, that 2.5 hours once a week, was confounded. If you were to redo the experiment, what would you have to do to remove this confound? To make all things equal? You have to put the weightless control group in another meeting that was about something else, or you could try saying, you can go take the afternoon off. Take the 2.5 hours and go do something else. But whatever the solution is, you have to equate the two groups. They were not equated. There was this confound there that's kind of part of the problem of interpretation, really, ultimately. Now, the question that everybody's going to have to live with is, was that enough to invalidate the results, ultimately? There are enough other studies out there that suggest that meditation changes people's brains, it changes people's mood, it changes people's immune systems, that at this point, that question is, even though there was this confound, it wasn't the explanation for the results. Okay, so what can we causally conclude from this study? Not a lot. What we can causally conclude is that participation in a positive change group context like this on meditation creates positive changes in people's mood, their brains, and their immune systems. It didn't compare alternative treatments. It didn't compare stress reduction, other kinds of stress reduction interventions. It didn't compare psychotherapy. It didn't compare exercise. You could have had people go to the gym once a week. Maybe similar results would have occurred. Who knows? But we do know from this that there was something beneficial occurred from the intervention, and that it might be that those results will hold up. Now, in general, in all of science, there's measurement bias. Bias is a particular kind of systematic error. There's two important kinds of bias in psychological studies: sampling bias and expectancy bias. How do you measure and how do you minimize these biases? Well, first of all, you need to randomly sample from a representative population, which hardly ever happens, because a random sample is a true random sample of the population of the world would be what? Every single individual in the world has an equal chance of being included in the study. That's what that would mean. Now, that's insane. That's just not going to happen. Okay? So usually what you do is you try to kind of overlook the random sampling side of it, and you try to say, is my sample good enough? But ideally, you want to have a random sample from a representative population. A representative population is a population that fits what you want to talk about. You want to get a high response rate if you're doing a survey, and you want to be very particular about what you're going to conclude. I say specify your generalization targets. What I mean by that is that you should limit your inferences to the group that you've studied. That's simply what I mean. Limit your inferences to the group that you're studying. Now, here at the University of Wisconsin, you guys are not a randomly selected sample, but you are, if you are involved in experiments, you will be randomly assigned to experiments, not to experiments, but to experimental conditions. Typically, you sign up for experiments, so you're not randomly assigned to your experiments, but if you are in a study, you're going to be randomly assigned to a treatment group if it's a true experiment within a particular laboratory. That's the essential point of this slide. Now, are you a representative of the population to which researchers want to generalize? This, again, is one of those little dirty secrets of psychology, psychological sciences, that people overlook this all the time. Well, probably they want to talk about people as a whole, and you're pretty good, as it turns out, for most purposes, you're a pretty good approximation, but you're not, in fact, truly representative. And real good studies limit their conclusions to the kinds of persons that were studied. You are a convenient sample. Good research based upon your data will talk about university intro-psych students being the population that are being generalized to. Now, an expectancy bias is a bias of somebody or other having an expectancy. It's systematic error resulting from a belief, which is what an expectancy is. It's a belief of one kind or another. Two kinds of expectancy biases that we have are observer expectancies and research respondent expectancies. And here's how they're handled. Observers, or the experimenters themselves, often have biases that they bring to bear on their studies. And that when you as a researcher are doing something to affect your data, even though you're not doing it knowingly, you're engaging in having an experimenter expectancy effect. One of the classical studies of this problem was animal experiments, testing a drug effect. You need to be able to know which group. Let me see, what did I do here next? The study I'm going to show you is a little bit different. Here's the example. Students are given randomly a group of rats. One group of students is told, your rats are really good at solving mazes. They're going to be good maze-solving rats. The other group isn't told that. It turns out that the students who had that expectancy, my rats are fast rats, their rats won. Were they actually any better? No. They were the same rats from the same litters. So people's beliefs, experimenters' beliefs, affect their data. This is why we have to, in studying things, so there's observer expectancies and subject expectancies. Subject expectancies are when the students themselves, the research participants, have beliefs about the research that affect the outcomes, really, ultimately. How do we control these things? Ultimately, we need to minimize experimenter expectancies and minimize subject expectancies. And ideally, it's blind experimentation and an effort to keep subjects blind to the purposes of the research. Ideally, double-blind studies are the best, but that's really quite hard to do. And that when you can't blind your studies, you teach experimenters to be consistent. You give subjects instructions, which you'll all get in the studies that you're going to take. And sometimes you can compare different instructions, ultimately. Okay? I think, generally, conclusion-wise, to sum up, we want to control sampling and expectancy biases to get good research. In general, descriptive studies, case studies, surveys, naturalistic observation. Hang on, guys. Just let me finish, please. Correlational knowledge is a great start, but you have to do experiments to get causal understanding. Okay? We'll just leave it at that, and see you guys next time.